So, for our thermochemistry, we have covered heat. We have covered heat being transferred. We have talked about, we defined enthalpy, which is the total amount of energy in a system, and we can calculate the change in enthalpy. And in our last discussion, we talked about how if we know the energy, the enthalpy of a reaction, that we can figure out how, we can use stoichiometry to figure out how many grams of something we used, or how, if we know the grams, how much energy it's going to produce. Today we're going to talk about enthalpies of a reaction and something called standard enthalpies of formation. All right. If you look in your textbook, in the online textbook, or if you Google online, you can find a heat of formation table. And in the textbook, it looks like this, table 7.5. These are values of the energy required to create 1 mole of the substance given. For instance, bromine, it takes, oh, I can't circle it because it's not in my program. It takes 1 mole for bromine, it's the top one there, 111.9 kilojoules to make 1 mole of bromine, a single bromine atom as a gas. So that table, there is a very shortened table in your note packet that you have, that I've sent you virtually. There's a table in the back of the textbook. I'll show you how you find that. You go to table of contents. Down at the bottom it says back matter, appendix 2. And B, standard thermodynamic quantities for selected substances at 25 degrees Celsius. All right. So that is another place you can find these. All of these have been given to you in the equations, at least the ones I'm using. And you'll have access, and on the online ones too, they're there. So you'll have access to what you need. But I just wanted to show you where that was. Okay. Back to this. A couple things you have to understand. The definition of what we call standard state. If you're talking about a gas, the definition, the standard state is a gas that's at a pressure of 1 atmosphere, meaning the pressure, average pressure you would be under at sea level. If you're talking about a liquid or a solid, your standard state is for a liquid or solid, is the pure substance in its most stable form at a pressure of 1 atmosphere and a temperature of 25 centigrade. And for a solution, it would be of 1 mole of molarity. I'm cutting my head off. Sorry. Standard enthalpy change is the change when all reactants and products are in their standard states. The degree sign tells us the standard state. And by degree sign, what we mean is you're going to see something. That's a degree sign. The standard enthalpy of formation, we have a little f for formation. If it's a reaction, we have an RXN. Now, if you're talking about a pure element, remember when we did the oxidation numbers, pure elements had an oxidation number of 0. When we're talking about something in its standard state, if it's a gas in its standard state, then it's going to be 0, have a 0 energy. So if you have got O2, which is a gas, at its standard state, it's going to have a value of 0. Whereas the bromine I showed you before, it was just a bromine with 7 electrons, or 9, I don't know however many electrons, but not attached to anything. Bromine, you know, is a Hofbrinkel. It normally comes attached. So bromine like that would be a 0. But if you have bromine that is simply by himself, you'll need to put in 111 kilojoules in order to get that. All right. So if you've got a standard state of enthalpy for a element, it's going to be 0. So when we're talking gases, it's got to be at a pressure of 1 atmosphere. If we're talking liquids or solids, it's going to be what state they're in at room temperature, basically, which is 25 degrees Celsius. Okay. Otherwise, the compound's what we look up in a thing. So first, we're going to talk about standard enthalpies of formation. What we're talking about is the energy involved in order to take all the particles apart and put them back together and make 1 mole of the compound. So if we start with MgCO3, what makes up that compound? Well, magnesium does, and carbon does, and oxygen does. Okay? Those are the pieces that make up magnesium carbonate. Now, we have to balance that. So, in order to balance 3 and 2, we'd put a 3 here, and we'd have to put a 2 out in front of that, which means a 2 there and a 2 there. Well, that's all very well and good, but when we look up the heat of formation on our table, we're looking it up for 1 mole. How many moles is that? That, my friends, is 2 moles. So, we need to do it for 1 mole. So now, how am I going to get that to 1 mole? If I divide everything by 2, now I have 1 here, 1 here, and 3/2 of an oxygen. Okay, which is 1.5 oxygen, moles of oxygen. All right, so that's our ultimate equation. Okay, and now we need to look up the value for magnesium carbonate. So I've gone to the part in the back of the book, and I can try to zoom in, but then things get fouled up, so I'm not going to. Believe me, this is not the first take for this video. But magnesium carbonate in here is negative 1095.8. And our units are kilojoules per mole. Okay? Let's do the next one. The next one, C6H12O6, glucose, our old favorite, would be carbon plus hydrogen plus oxygen All right, we would need 6 carbons, we would need 6 hydrogens, and we would need 3 oxygens. Okay, that makes 1 mole of glucose. So let's look up our heat of formation back on our lovely chart. And for that starts with carbon, so we're going to come up here to carbon and look for glucose. Say 1206 right over here in the middle, 1273.3. Meaning, if you were to create glucose out of all of his basic particles, his elements, you would give off 1,273.3 kilojoules for each 1 mole you made. All right. The next one, write equations for the formation of sodium chloride from its respective elements. Okay, sodium chloride. I'm changing fonts here, or colors, and it's changing. All right. That's what our equation would be. There, now it's not taking up so much space. We only have one chlorine, so we're going to write this. Normally we would balance this and have 2 sodiums and make 2 sodium chlorides, but instead we're going to say 1/2 of that chlorine. So we're going to make, we'll have 1 sodium, 1 chlorine, making sodium chloride. We look it up in our table. We'll come down and find sodium. Mn. Oh, sodium starts with an S. Duh. Sodium chloride, solid. It's down here right at the bottom. Can you see my little pointer thing? And it's negative 411.2. .2 kilojoules per mole. The other one, lead nitrate. So we're going to make it from lead, which is a solid at room temperature, nitrogen, which is a gas, and oxygen, which is a gas. We need 6 oxygens. I'm going to balance it out first, and then we'll get it down to 1. I need 6 oxygens. I need 2 nitrogens. That works right there. So we don't need to have any fractions. Lead nitrate. Lead starts with an L. It's right here. negative 451.9. Negative 451.9 kilojoules per mole. Okay? And the first 2 questions in the online homework are just simply having you, actually the first 3 maybe even, are simply having you doing equations like that. Now, if we know the energy of a reaction, or we want to find the energy of a reaction, what we're going to need to know is heats of formation. And the general way that this goes is you take products minus reactants. All right, you're going to take the sum of whatever the coefficient is of the products. So if we look at the lead one, no, that won't work because that's a heat of formation. Let's look at this guy down here for an example. What are our products in this case? The products are nitrogen monoxide and water. So we're going to take the sum of the products. We have 4 nitrogen monoxide molecules, so we'll take 4 times the energy of formation, the enthalpy of formation, and we'll add to that our 6 waters, 6 times the enthalpy of formation of the water. And then we're going to subtract the sum of all the reactants. So our reactants are the green guys down here. Our reactants, we have 4 NH3 and 5 O2. Now, what did we say about gases? Elements are always going to be 0. So this one's going to be 5 times 0. That's simple. So we need to look up 4 ammonias that are gases. NH3, 45.9. Waters, and our water is a gas because there is one for gas and there's one for liquid, and you actually have to know the difference. rather than go look it up, I've just looked it up for you so that we don't spend a whole lot of time watching me flip through the index in the online book. So we have 6 waters that are gaseous, and the value for that is 241.8. And for nitrogen monoxide, it's 91.3. It's a positive, not a negative. So now we just do the math. We're going to sum all of this. So 91.3 times 4 is, all right, had to reshoot that. So 91.3 times 4 is 365.2. 6 times 241.8 is negative 1450.8. And then we're going to subtract 4 times negative 45.9. And we get negative 183.6 plus 0. All right, subtract something that's negative, you end up adding them. So we're going to take 183.6 plus 365.2 right here minus 1450.8. And we get negative 902 kilojoules. Okay? Next one. And we just did that. So we did products minus reactants. Okay, so again, same story. Products minus reactants. Okay, so same story here. We're going to take the products minus the reactants. Our products are going to be, we're going to take the sum of aluminum oxide, and I just looked it up. It's negative 1675.7, and there's only one, so we don't need to multiply by anything. And we're going to add to that 2 irons. That's iron in its elemental state at a solid at room temperature, so it's a 0. And then we're going to subtract the reactants, and that's going to be 2 times the aluminum, which is a 0, and iron 3 oxide, which is negative 842.3. And only one of those, so again, we don't have to multiply by anything. So this guy's pretty straightforward. 1675 minus a negative 842.3. So 42.3, we get negative 833.4 kilojoules, which it's going to be this one. Obviously, I've done something wrong in my calculations. I didn't transpose some. I probably transposed a number, but close enough. Okay. And if you're on the online book, this is actually a problem. All these are out of the online book in that section. It's section, I don't remember which, section 7.9. Yeah. All of these are out of the online book. And this particular one is interactive. You can click it in the book and it'll tell you whether you're right or not. All right, the next one. Now we've got a more complicated one. I'm going to stop here. I'm going to set this one up as extra because there's none of this in the online stuff, so you don't need to know how to do this. Go ahead and do the enthalpies of formation section online, and I'll put this one together as a separate video so you can do it if you want to see how. It's a little confusing, but we can figure it out. and I may put together some kind of a worksheet. I've got several in that heat packet that I put on Classroom that we can use to practice with if you want more practice other than the online stuff. I'm doing this out of the book, the online book, rather than from my data that I usually use, because this is the way the final is going to be. And I may be creating a whole new system for next year. Who knows? Thanks, guys.